This conference will now be recorded.
Okay. Good morning, guys. So yesterday we have we have been discussing about the training other models, and as part of that, we have completed many important concepts within the process of training the model. I have very clearly explained you how things will work in the normal equation, and we also discussed about the computational complexity in normal equation. I explained you what happens and how the gradient descent will work, and imagining that you are at the top of the hill and you wanted to come down. What happens when you are at the current position and how it works when you wanted to move to the bottom of the valley. In that process, we also taught about the learning step and the random initialization. The random initialization will always be starting with 0. I also told you about what happens if the learning rate is too small and what happens if the learning rate is too high. If you have not completed yesterday's use case or yesterday's class, kindly please watch it, understand, make a notes, and then move on to the next one. I've been telling you the same thing from day one, that if you don't attend one session, the corresponding next session wouldn't be so easy gel with you. Okay. Now, let me take the next one, 33. Here I have very clearly explained about what is global minimum and local minimum, how things works in global minimum, and when do you achieve the global minimum in the form of Plato. And if Plato is on the left side, if you approach, how things will work. And if you approach Plato on the right side, how things will work. This is what we have been talking yesterday. I also explained you about global and local process, the convex function, and we discussed about future scaling also. We also discussed about what happens when the system is too complex and how the model will try to look at all the various angles. When it look at the various angles, the algorithm will search for more dimensions. When it is trying to search for more dimensions, it has more features, and it also search becomes complex. So this is what we have discussed yesterday. So now let me jump on to today's session. Today we are going to talk about gradient descent with other algorithms. So guys, in this process, we will be discussing more importantly about stochastic gradient descent, batch gradient descent, and mini batch gradient descent. Okay, what is the need and necessity of? Let me see if my screen is shared, and let me see if you can. Yeah, perfect. You can see what I write on the screen. Perfect. That's what I want. Now, in here, what happens is you have batch gradient descent, you have stochastic gradient descent, and you have mini batch gradient descent. Now, why are we looking at various options within gradient descent? What is the need and necessity? Because gradient descent has got various options which you can implement based on the need, based on the use case. For that reason, you must be familiar about batch gradient descent, stochastic gradient descent, and mini batch gradient descent. If you remember carefully, we have completed the SGD in our first use case. Today, we are going to learn and understand why and what made us to use SGD at that point. All the silly questions, meaningful questions, and idiotic questions that you have when we did it on that day will be cleared in this module. Okay, so kindly please focus. Now, batch gradient descent is also called as partial derivative. Why? It is called partial derivative. You are deriving something partially. Okay. Take an example. If you initialize the model parameter theta 1 and theta 2, you need to first initialize it. You know about random initialization, which I have told you just a few minutes back in the diagram. Okay. From that random initialization, to finalize the model parameters theta 1 theta 2, for each of the weights, we change one weight and keep others fixed and calculate the change in cost. Again, change in cost is all about reducing the MSE. We know about it. Now, when you are focusing on changing one weight and keeping all other fixed is partial functionality. Once that's done, it moves on to the next weight, changes that second weight and put all other weights fixed and calculate the change in the cost. Once that's done, it moves on to the third weight, changes the third weight, put all other fixed, puts all of the fixed and then calculate the change in the cost. Like this, when it is trying to make a change in one of the weight and putting all the fixed is called partial derivative. Okay. Partial derivative can be understood by what is the chance of going down of the valley from the top if I'm standing north or if I face the east. Likewise, it is asking the same question, what is the slope of the mountain under my feet if I stand in the facing north, and so on in all other dimensions. That is called batch gradient descent. Okay, please remember this. Simply, in a nutshell, if you wanted to remember that carefully, batch gradient descent is all about partial derivatives. Okay, now erase all the drawings, go back to the pointer. Now, partial derivatives, cost function, further explanation with batch gradient descent. Okay, now in general, if we compute the gradient of the cost function with regards to each model parameter called as theta j. Below is the equation for finding the partial derivatives of the cost function with respect to parameter j, theta j. Now, with this equation, when we try to calculate the partial derivative of theta j individually, instead we can compute all of them in one go. Okay, do not break your head and do not worry if looking at the complexity of the formula, but we have already broken it. In this, you have theta of t. Theta is a model parameter. Theta of the t is the transpose of model parameter. Bold small x is the vector, and y of I is the predictions of that particular instance, and x of j of I is model parameter of ith instance with with the partial derivative cost function. Okay, that's the mean square error formula. So in this slide, all you need to remember is to calculate the gradient of the cost function, you will be focusing on the each model parameter value theta of j. Okay, like that. Below is the formula that is calculating the cost function gradient descent at mini batch. Perfect. When you are trying to calculate the partial derivative or batch gradient descent for each parameter theta j, instead we can compute all of them in one go. How? Just make change for one, get the calculations or get the change in score, and you can just take that first one as a reference and implement that on second one. Again, that is also a theory concept which you must be aware of. That's all you need to know here. Now, the next one is continuation of batch gradient descent gradient vector. Now, guys, think about it. You know what is a vector? you know what is a matrix. Vector is the small x which is bold, and 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 the uppercase X is all about a matrix. The gradient vector is all about the one that is containing all the partial derivatives of the cost function. What did I say just a minute back? I told you, boss, change the value of the, let me take a pen here, change the weights of the first one, rest all are fixed, calculate the change in cost. First one, this is 0, like that. Change the value of the weights, put all of the fixed, and calculate the change in the cost. Change the weight of the change the weights of the nth one, put all the fixed, and calculate the change in the cost. So in this way, the gradient vector, you know what is a vector, right? The gradient vector will contain all the partial derivatives of the cost function. This is what it is. Perfect. One for each model parameter. Again, this is for 0, this is for 1, this is for n. Like that, it contains the values of the n parameters. This formula involves calculations over full training set at every step. Now, you have split your data into training set and test set. This is training, TR, this is test, TE. For example, I'm saying. Now, this gradient vector of batch gradient function or batch gradient descent, this involves the calculations over full training set. This is your full training set, okay, at every step. This is why the name is called batch gradient descent, okay. The name itself says batch gradient descent. The formula involving calculations over the training set X at every step. And in every step, it is trying to change the value of the weights and then coming up with the results. Okay. And finally, it gives the results of all the changes. Okay. Now, since every batch gradient descent uses entire training data at every step, it is terribly slow on large training sets. That's quite obvious now. But the gradient descent will scale well when you scales well with number of features. Now, if your training data is high, you may potentially have a delay in vectors calculation or calculation of scores from the batch gradient descent. But it also does well when you have thousands of features. Now, it is always easier to train a linear regression model when there are thousands of features. Using the gradient descent than using the normal function will always be beneficial for you. Look at my last sentence. It is faster to train a linear regression model when there are thousands of features. Okay, when there are thousands of features. If you have many number of features, using the gradient descent and the normal equation will help you. Now, let's quickly recap what you have understood from the batch gradient descent. Batch gradient descent is also like stochastic gradient descent, but in batch gradient descent, you are calculating the each model parameters theta j and then giving the values of or giving the results of the change of weights for each individual component. Within this, your batch gradient descent is doing the calculations all over the training data, and that could be the reason why it can go slow. But on the other hand, it deals well if you have many number of features. So it is also easier and faster to train a linear regression model when there are thousands of features. For that reason, using gradient descent will give you more result than using normal equation. If you don't know this differences of normal equation versus gradient descent and batch gradient descent, you will tend to limit the scope of the implementation of the algorithms. So please be careful at that point in time. You need to have all the options open, and you need to have a fully loaded gun, and the fully loaded gun is all your thoughts. And all your thoughts is, why not gradient descent, why not normal equation, why batch gradient descent, why not mini batch gradient descent, like that. Okay, now let me go to next slide. Now, looking at this slide, we have to link the previous slide. The previous slide, I'm talking about the vector of batch gradient descent. Now, once you have got the vector of the batch gradient descent, which points uphill? Uphill means like this. This is uphill, and this is downhill. Okay. Now, once you have the gradient vector, which points the uphill, just go in the direction opposite to the downhill. We can calculate the size of the downhill using the below equation. Again, we have the learning rate here. This learning rate will influence how fast you need to go down or how fast you need to change the direction. Again, folks, as I told you yesterday with explanation, let me take a pointer. If you see here, I have very clearly, nicely explained you what happens if you wanted to come down from the top of the valley to the bottom of the valley if you are stuck in the dense fog. And I also told you what is the importance of the random initialization value and how that random initialization value plays a key role as well. And I have shown you a couple of diagrams, and in those diagrams I have shown you the learning rate as well. So if the learning rate is too small, this happens. If the learning rate is too high, this happens. Okay, 1 second, let me not mess up the diagram. Now, I also shown you here the local minimum and global minimum. When you are focusing on local minimum, when you need to reach the local minimum, at times you first cross the global minimum and come to local minimum. And at times when you want to reach the global minimum, you have to cross local minimum. You may have plateau on the left hand side, or you may deal the plateau to the right hand side. Machine learning is all about giving all the permutations, combination, experimenting the attribute combinations, and knowing and applying each and every that's logic. Okay, that is what it is. Now we understood this one also. This is the gradient vector, formula. This always points the downhill, and you also need to know the equation. At times, if you have got the gradient descent which points uphill, just go and check what happens if you go the downhill also. Okay, there's nothing to remember in this, but you need to know the important functionality. Now let's do some hands-on. Very important. While doing hands-on, please try to spend an extra minute to understand what each line of code is doing. Theoretically, we are breaking each and every nut and bolt and fixing it back to get the flow. Likewise, I would recommend you to please focus and do the practicals also. Okay, so now let me do some practicals and let me show you what I'm trying to do here, guys. Now, here what is happening is we are discussing about quick implementation of algorithm, and in this process we are going to apply the batch gradient descent on our process, on our data. Okay, first let's understand the code and then see the results. Okay, I'll take the pointer here, or I'll take the pen. Okay, first thing, you need a learning rate. So I have given the learning rate as 0.1. First step is done and dusted. You understood. Number of iterations equal to 1000. Okay, number of iterations equal to 1000 means number of iterations after which algorithm will stop. Guys, Training of the data is nothing but stress testing the data with number of occurrences you have, and it learns from each of the occurrence. First occurrence, I got this. Second occurrence, I got this. Occurrence is again instance. Instance is again number of different features you have. This feature, I got this one. 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 But ideally, this is what I'm expecting for. So when you talk like that, when you focus on getting the derivatives, you need to know at which step the iterations will stop. So that is the number of iterations, and m equal to number of elements in the training set. When I say m equal to 100, number of elements. If you have 100 records, that is 100 elements. Again, do not tend to confuse between number of elements and number of instances. Number of iterations is nothing but one time, two time, three time, four time, five time, six time, seven time, eight time, like that 100 times. Again, number of elements is nothing but number of records you have. So on 100 records, you are doing 1000 iterations. On 100 records, you are doing 1000 iterations, mean you are learning 1000 different examples on the 100 records. That is the beauty of it. Machine learning by itself with perfection. It goes and senses in each run how the model is training and what is the prediction. And from there, you get the scores. You minimize the mean square errors. And in the mean square errors also, you can get a more idea on batch gradient descent or gradient descent, or at times you can simply do the cross validation also. Okay, there are different approaches you need to follow, but as a machine learning engineer, you must know each and everything carefully. Okay, so this is also done. Now, random initialization of model parameters. This one I have already showed you the importance of random initialization. As the learning rate is 0.1, you need to start the random initialization of the model parameters also. Okay, now here what happens is you have used a for loop. For loop for iterations in range of n underscore iterations, which means for iterations in range. How many iterations you have? 1000 iterations. For iterations in range means for each iteration in each run, go and apply this formula for me. This formula is nothing but gradient descent equal to 2 by m into x underscore b dot t dot of theta of y. Again, this formula is available on the Google when you say gradients formula. Now this is gradient vectors of the cost function formula. Once I run that, I'll get the theta, which is what theta is equal to theta minus eta into gradients. Okay, again, this is also available on the Google when you say gradient vector formula. Okay, this is same like a normal equation, but what difference between normal equation and gradient descent gradient vector is that you need to find a distinguished process which will benefit you, either to use normal equation or to use gradient descent vector equation. Okay, hope you understood. Now this is the practical part. I have run this on my Jupyter notebook also. Let me show you that. Give me 1 second. I'll go back to the pointer. Good morning, Kavi. Thank you for joining me. I appreciate your commitment. Great. Let me go here. Let me erase all the drawings. Let me go back to the pointer. Okay, this is the example. Earlier, first I need to implement it. And if you see here, ETA is a learning rate, iterations is number of iterations where the algorithm have to stop. M equal to 100 is your 100 records, and you are doing a random initialization of the numbers for theta, where theta first starts with a random number, that is a random initialization. And for 1000 iterations, you are applying the gradient descent formula, which is this one I have explained you. And then your theta value is nothing but theta minus eta into gradients. Okay, this is the formula. When I just say theta, then this is the value I got. Perfect. Now let's take this one. How the learning rates affects the gradient descent. Learning rates are very, very important, because if you look at my diagram here carefully, folks, now the first 10 steps of the gradient descent using 3 different learning rates. Okay, when I say the first 10 steps, the way how things will work in the first 10 steps. Okay, 2 3 4 5 6 7 8 9 10. Okay, 10. Here you have 10. Here you have only 0.1205 and few things, one gone here and one gone here. Okay, that's fine. Now try to understand carefully what happens if you go up, what happens if you go down, what happens if you are at middle is already been discussed from the top of the mountain to the bottom of the valley. That is the thing we discussed. 1 minute, let me go back and relate that concept with this one. Where is that beautiful diagram? See, look at this. This is the gradient descent linear regression. Now we are talking about batch gradient descent regression. In batch gradient descent also, the learning rates are very important. The dashed line represents the starting point, and the rest of the things are the gradient descent with each different learning rates. Here, like I said earlier, we are distinguishing with a in learning rate equal to 0.02, learning rate about 0.1, and learning rate about 0.5. So let's see the difference of each one and understand how things works there. Erase all the drawings, go back to the pointer, just do this one. Now look at this, guys, understand my approach. If learning rate is very low at 0.02, okay, I'll take a pen here, I'll take a different color, I'll take dark green. I'm talking about, let me take a pen again because it's not taken properly. I'm talking about this one now. In here, my learning rate is too low. When the learning rate is too low, algorithm will take a long time to reach the solution. Do you see this? It has taken so much time. These are the lines it predicted. These are the lines, these are the actual lines, and these are the predicted lines. Again, it has taken a lot of time to reach there. Now, if learning rate is good, this use case, in few iterations only, it will converge to good solution. There is no big gap here. This one and this lines are actually in almost in line. Now, if learning iteration is too high, if it is too high, see the difference between actual data and predicted data, and they are nowhere in sync. They are nowhere in line. Now, this is jumping. Algorithm is getting diverged, means getting away from actual versus predicted, jumping all over the place. When I said jumping all over the place, means there's a lot of difference, getting further and further away from the solution every step. See, it got away like this, away like this, away like this, away like this. So this is the actual data and this is the predicted data. it is slowly coming away from the prediction. Rather, it should go very close to the prediction. This is the importance of the learning rate. Now you can link this one with the learning rate of the gradient descent from starting from the top of the mountain valley to the bottom of the mountain valley, and every step you take will be an learning example. If you come down fast, that is one use case. If you come down slow, that is one use case, which I explained you in a bumpy scenario. Let me show you the diagram once so that will make sense to you on where I am focused. Look at this. Here I told you in gradient descent learning rate what happens if the learning is too small and what happens if the learning is too high. Like this, it can be batch gradient descent, it can be just gradient descent, it can be polynomial regression, it can be regress regression, it can be softmax regression, any regression. You need to know the learning rate of each of the thing. You need to know the vector of the learning curve of each thing, and that's how you tend to become a matured and technical hands-on data scientist. Okay, hope it's making sense to you. Hope you now, if you go and open the machine learning project, first one we did, you'll have answers for all the questions that break your head at those days. Okay, that's the reason why I have taken this approach. First, I know you don't know swimming. I want you to throw, I wanted to throw in a swimming pool, struggle yourself hard and understand the uh, depth of the pool and the difficulty of learning swimming. And when you are almost stuck there, I'll pick you up and then teach everything and then dump you again. That's my approach. Okay, perfect. This is also done. Now let's understand. Now you told very, we discussed very nicely about the learning rates. We also discussed about iterations, but you also need to know what is the best decision you can make with how many set of iterations will give you a good result. That is also very important, right? So we are going to discuss now. In previous example, you took 100 elements and you took 1000 iterations. What made you to think like that? How do you think that will give you the good results? You need to understand that. Okay, the first one is how how to set number of iterations and find the number of iterations. Guys, I'm here, I'm here. I'm just thinking something. Okay, let's jump back. Now, how do you come to understanding that number of iterations you need to have? How do you find the number of iterations? Now, if number of iterations are too low, then they may not get optimal solution when the algorithm stops. Guys, in machine learning, more iterations you have, more examples you learn. From more examples you learn, more predictions you get. From the more predictions, you can choose the best prediction. That's how it works. Okay. Now, if the number of iterations are too high, then our time may be wasted and algorithm may never converge. When I say never converge, it will never take enough time to reach the actual data versus predicted data or predicted value. Now, how do you find a good learning rate? So number of iterations is also important, number of features are also important, and the learning rate is also important. You need to be very smart in probabilities, permutations, and combinations of these three things so you can reach the best optimal solution. Now, how do you find a good learning rate solution? Set a very large number of iterations. If you have large number of iterations, then it will help you to find a good learning rate. Interrupt the algorithm when the gradients vector becomes tiny. When I say tiny, again, when the gradient vector value becomes minimum, stop it there. Interrupt it. Don't stop it, interrupt it. Now, when you interrupt it, you'll get the norm of the gradient vector becomes smaller than E tolerance. Again, E tolerance is nothing but your random initialization value result versus next random initialization value results. You do different iterations, right? The first iterations random initialization values output versus second instance random initialization value. Considering all this, you will get a tolerance value. The norm of the gradient vector will become smaller than that tolerance value. It's just a theory concept. Don't break your head much. Basically, this is the norm of the vector formula. This is the norm of the vector formula, and interrupt the algorithm or stop it when you see this one. This is called as E tolerance, and this E tolerance value, the norm of the gradient vector should be small than the E tolerance. We'll talk about the E tolerance more detail in future subsequent sessions, but for now, remember, to get a good learning rate, you need to have the vector gradient vector value becoming less than or smaller than the E tolerance. And you also know the norm of the vector. Norm of the vector is nothing but norm of the gradient vector. Norm of the gradient vector is again the formula which I've just shown. In this slide, we covered how you can get the good learning rate and what happens if the number of iterations are too high and what happens if the number of iterations is too low. Okay, that's what it is. Erase all the drawings, go back to the pointer. Now, convergence rate for the batch gradient descent. Now, what is a convergence rate? Convergence rate is nothing but, boss, again, let me go back to this diagram. Time taken for this time, how fast it converges to the actual date value versus predicted value. Here it converges so fast. Here it is okay, but unfortunately it's going away from the actual data versus predicted value. Okay, erase all the drawings, go back to the pointer. Now, in this diagram, let me check the pointer properly again, it's not highlighted. Now, again here, that's the convergence rate. The convergence rate can be defined as, for mean square error, the batch gradient descent with a fixed learning rate has a convergence rate that is equal to, if we divide the tolerance by 10 to have a precise solution, then algorithm will have to run 10 times more than iterations. Again, this you'll understand when I explain you more practically about the tolerance European symbol. This one I'm talking about this one. Okay, but just remember the convergence rate is important, the learning rate is important, the number of iterations is important. Slowly you are combining all the important aspects of machine learning project and getting your gun fully loaded. Earlier we don't have that idea, now you don't have idea, I have it. So now we are trying to put everything in one paper and making an approach on what to take, how to take, how to deal with it. Okay, so convergence is nothing but the amount or the formula implementation versus how you can reach the convergence faster. Convergence is in linked with your number of iterations, number of features, and also learning rate as well. That's what it is. Now let's talk about the stochastic gradient descent. All this while we have been talking about batch gradient descent. The problem with batch gradient descent is it is slow when the training set is too large. As the batch gradient descent uses the whole training set to compute the gradient at every step, it is a bit slow. The stochastic gradient descent, what it does is it just picks a random instance in the training set, and at every step it trains. It computes the gradient based only on the single instance. Perfect. This makes the algorithms much faster. As little data gets manipulated at every iteration. We have been talking about gradient descent, but you also need to know the differences between gradient descent and batch gradient descent. As a batch gradient descent is slow when training set is too large. Okay, and it uses the whole training set. But stochastic gradient descent will pick a random instance and trains on that at every step. When I say every step, in this, every iteration, the instance on which the iteration is running, and the learning rate and the convergence rate. Okay, this computes the gradient descent based on the single instance. This makes the algorithm much faster. Okay, because a very little data is manipulated. Why are you saying very little data is manipulated? Because the data, it is only picking one instance and making changes on that instance's data. Now, also huge training set to be trained. As only one instance need to be in memory at each iteration, you can try and train huge training set to get the best predictions. Okay, that is the difference between stochastic gradient descent and batch gradient descent. Look at the diagram on the right side, how it is linked and how it is reaching to the inner circle much faster. Okay, let me go to next slide. Here, stochastic gradient descent. Again, this is a continuation. Go and link what you have learned from the batch gradient descent in the gradient descent, stochastic gradient descent. Instead of gently decreasing until it reaches the minimum, the cost function bounces up and down, decreasing only an average. Perfect. We explained it in two scenarios. What happens if you approach the plateau on the right side, what happens if you approach plateau on the left side, and what happens if you take a different approach. Now that's the cost function bouncing up and down, decreasing only on average. Over time it ends up very close to the minimum. We understood that, but once it gets there, it continues to bounce around, never settling down. I told you, right? It gets the local minimum, but that's not the end of the story. It bounces up and down, again goes to global minimum and gets there. But once the algorithm is stopped, the final values, when will the algorithm stop? Algorithm will stop when the final parameter value is good but not optimal. Also, the algorithm will never settle down. It only keeps trying to bounce and go to a different value to see if that can be a better prediction. Now, what happens when the cost function is irregular? Yes, the cost functions in most of the cases will be irregular. In that scenario, how as a data scientist or machine learning engineer, you will find an optimal way to solve the issue. Now, stochastic gradient descent has got better chances to find the global minimum than the batch gradient descent. Yes, I agree with that. Here, the randomness may help algorithm to jump out of the local minima. When it is jumping out of the local minima, as seen in the randomness in the stochastic gradient descent, it is good to escape from the local minimum. That is fine, but bad algorithm can never settle at minimum. The reason why simple was if your algorithm is not settling at the minimum, and if it is not settling down, and if it is continuing to bounce around, then that algorithm is not good for the use case. Or you can try reducing the iterations, you can try increasing the iterations, you can try increasing the learning rate, you can try reducing the learning rate. Parallelly, you can reduce the convergence rate, you can increase the convergence rate. After all doing all these things, if the algorithm is not settling at the minimum, then that algorithm is not different. At that case, then increase the complexity of the model or reduce the features, add more features, and that's how you have to do the more stress testing on top of it. With this one, we have completed the batch gradient descent and jumped into scototic gradient descent. If you look at the diagram, we are still here of this use case. We need to complete the polynomial regression and more regularized linear models and then jump to the logistic regression. Okay, we are online, we are in sync. We will be able to complete the target by the time we discussed and we wanted to finish the agenda. Okay, I'll upload this recording shortly. Thank you for joining me this morning. And to I couldn't continue the workshop today because I have got some professional, some office commitments at the venue we catch up. So I'm waiting for them to come back to me. And once that's done, we still have a lot of time. We can do our face recognition and emotions detection use case hands-on. But please, I know most of the guys are not turning up for morning sessions due to their personal, understandable reasons. If you don't practice all your pending sessions, you will slowly distance yourself from the subject because you lose interest, you lose the rapport, and you will hate to join the session because, however, you will not understand the next concepts because you haven't been able to complete the previous classes. When you don't complete the previous classes, your anxiety piles up. When anxiety piles up, that's a kind of discomfort. When you get into that discomfort zone, your subconscious mind will never let you come out of it because your subconscious mind know that's a pain. The anxiety is a pain. The anxiety is a pain that is created because you didn't practice all the sessions and you have to take one extra step out to finish all those pending classes. That is the reason why I always keep saying, I don't mind if you don't attend morning classes, but I would request you to complete that day's class on that day itself at any point in time when you get some time. Now, if you have three pending classes, three, 2 or 1 hours, and one is 2 hours, for you to sit and complete 4 hour session is a nightmare. As humans, we are not machines. We are not a CPU. You can max sit and focus on one session for 1.5 hours. For one day, max 1.5 hours you can sit and focus. Now what about the rest of two classes? Again, you have to wait for next day. Next day, you have new session coming up again. So don't fall into this trap and dogma. Plan your schedule properly. Take a pen, take a paper, write down what you have attended, what you have not attended, what are your pending topics which must be completed. Chalk out a plan and try to dedicate some time and finish it off and come back to with all the questions you have. I can confidently say this is the best way of teaching data science, machine learning. I have taken the slides from one of the best recommended book in the world of starting machine learning. And every concept I learned or I taught you, I have tried to break the nut and open the shell and give it to you. So it should be as easy as possible for you to link the things if you complete all the sessions. I'm not blaming anyone. Everyone have their own style of learning. Everyone have their own way of understanding and linking things. But all I wanted to say is I'm more than happy to help you if you're stuck. But maintain the tempo, consistency, persistence is very important. If you are consistent for 2 days and if you leave it on the third day, again make sure you come back on track by yourself. Talk to yourself. How confident am I? Am I doing well? Am I leaving something? Am I not confident, but I'm assuming I'm confident? Did I get all the
It's
concepts?
6 hours.
Did I get all the concepts clear to my mind? Think like that, and you'll find an answer for it. Everything we are discussing, we are doing practically, and the practical screenshots are also attached. So it must be straight away process for you to spend some time and understand the concepts. If you have any questions, please ping me on the WhatsApp. I'll see you all tomorrow. I'll send you the meeting invite and I'll also upload this recording shortly. Thank you, Kavi. Thanks a lot for joining me today. Have an enjoyable weekend with your family. Take care.